All right, chemistry, in this lesson, we're going to talk about the 5 types of intermolecular forces. So ion dipole forces are an example is table salt, which consists of sodium and chloride ions arranged in a lattice structure like bricks in a wall. This is an ionic bond. When a polar molecule, water, breaks the lattice structure of an ionic compound, NaCl for example, it is called an ion dipole interaction. So you see the salt crystal over there on the left, and when enough water molecules gang up on a sodium or a chloride ion, they pull it away from the crystal lattice, and that causes the salt to dissolve. That's why salt dissolves in water, and it dissolves into ions. So if you look at the triangle there, the positive hydrogen side of several water molecules, you can see the pluses, those are the hydrogens, are pointing toward that negative chloride ion, the green. And that's going to then pull that chloride ion away from that crystal lattice structure. There in that triangle, you see the negative oxygen side of several water molecules point toward the positive sodium ion, and then they pull it away from the crystal lattice structure. So both of these effects are due to ion dipole forces. Okay, dipole forces attract polar covalent molecules to each other. So these are both polar covalent because you have a highly electronegative chlorine and a not quite so electronegative hydrogen. So the chlorine pulls the electrons toward it. So hydrochloric acid is polar because a highly polar chloride atom pulls the hydrogen electrons towards it. Below, the positive hydrogen side of the HCl molecule is attracted to the negative chloride side of another HCl. So when you see these diagrams, the solid lines are covalent bonds. They are chemical bonds. The dashed lines are the intermolecular forces, which are much weaker than the covalent bonds. So the hydrogen on the atom on the left is attracted to the chloride on the atom on the right, and that's an intermolecular force. A third type is London dispersion forces. London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. Dispersion forces are how nonpolar molecules attract each other. Now, all molecules, polar and nonpolar, have London dispersion forces, but they're the only type of forces that nonpolar molecules have, and therefore they're very important when we talk about nonpolar molecules attracting. So let's look at 3 atoms down below, and there the electrons are just randomly going around the atom, and suddenly for some reason, and the reason could be anything, they settle over on one side, on the right side of each of those atoms. So what we see is that when the electron in the hydrogen atom on the left moves to the right side, it pushes the second atom's electron to the right. And if this effect repeats throughout many atoms, it creates a temporary polarity that attracts the atoms to each other. So you can see that the electrons, basically the right side of this molecule or this series of molecules is going to be negative, and the left side is going to tend to be more positive. In addition, the electron in atom number 1 is weakly attracted to the proton in atom number 2. That's the dashed line that you see on the left. And the electron in number 2 is to the proton in number 3. That's the dashed line you see on the right. So that is a London dispersion force attraction, and it is strongest the more electrons that a series of atoms and molecules have, then the stronger the London dispersion forces. So London dispersion forces, just sometimes called dispersion forces, are small but can produce a stronger attraction between large molecules with many electrons. So here we see CH4. CH4 is a small molecule. We've drawn Lewis dot structures and talked about it quite a bit. And it has weak London dispersion forces because it has only 10 electrons. If you do look at the Lewis dot for CH4, it's got 10 electrons. Methane has very weak London dispersion forces and is not attracted to other methane molecules because it doesn't have enough electrons to get pushed over to one side to make a particularly strong positive-negative dipole. Now let's look at a little bigger molecule. This is octane. That's a gasoline that people put in their car. And it's C8H18. And if you were to count the number of electrons in that molecule, there's 66. So this is enough electrons that is strong enough that if you push them over to one side, then they're going to create a strong positive-negative dipole in that molecule. And now if we get to an even bigger molecule, this is paraffin, that's candle wax. It's C40H82. It has 322 electrons. This many electrons form strong enough attractions to make paraffin a solid at room temperature. Because 322, you push them to the side, and then the next paraffin molecule, 320 to one side, and then the next one, 322, and the next thing you know, you've got a very strong intermolecular force between large nonpolar molecules. Okay. The shape affects the strength of London dispersion forces. Longer, flatter hydrocarbons, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules, such as the ones on the right, because they fit together tighter with less space between them. So you can see how the molecules on the left will lay flatly on top of each other, very close together, and that will cause the London dispersion forces to be stronger. Whereas the ones on the right, they're round, they don't fit together very well, and so they have weaker London dispersion forces. Okay, the next one is really the most complicated one. It's called a hydrogen bond force. Now, it's a misnomer to call it a hydrogen bond because it's not a chemical bond like a covalent, ionic, or metallic. It's an intermolecular force, so I tend to call them hydrogen bond forces a lot of the time. So here's the rule for hydrogen bonds. For a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine, no other atom, and must be attracted to the lone pair of another nitrogen, oxygen, or fluorine, no other atoms. It can mix and match, but it has to be that exact combination. Okay, so let's look at this intermolecular force. Here, the hydrogen atom on a water molecule hydrogen bonds with the lone pair on a nitrogen atom. So you can see the proton on the oxygen, so it's attached to an oxygen. It's attracted to the lone pair on a nitrogen. That's one of the three atoms that's legal, and so that can hydrogen bond. Over here, we have a hydrogen atom on a nitrogen atom. Hydrogen bonds with a lone pair on a fluorine. So you see that the proton on the nitrogen down there, it's attached to a nitrogen, so that's legal, and it's attracted to the lone pair on a fluorine. Fluorine is one of the three atoms, that's legal, so that can form a hydrogen bond. And then over on the left, you see two water molecules, and the proton on one of the water molecules attached to an oxygen is attracted to the lone pair of another oxygen, so of course that's legal to hydrogen bond. So hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton is left sticking out. So you think about that. Oxygen really pulls the electrons in the covalent bond with the hydrogen towards it, and that means that proton, the nucleus of that hydrogen, really sticks out and therefore can be attracted to the lone pair of another nitrogen, oxygen, or fluorine. Okay, now here's an AT question, and this will ask you to analyze all four types of intermolecular forces. So Lewis diagrams and boiling points in the isomer ethanol and dimethyl ether are shown below. Explain the difference in the boiling points of two substances using principles of molecular structure and intermolecular forces. So the first thing you notice is that ethanol has a much higher boiling point. What that means is you can automatically infer that means it has stronger intermolecular forces between it. Not between these individual atoms, those are covalent bonds, but between different ethanol molecules. Their intermolecular forces are going to be stronger because it has a higher boiling point. So why? Well, let's think about the different types of intermolecular forces. Both of them are about the same size, so they have about the same number of electrons, and electrons are what determine the strength of London dispersion forces, and so that's not going to really be an influential factor on why ethanol has stronger intermolecular forces, so we can scratch that one. Now, what about dipole-dipole? That's between two polar molecules. Well, if you look at the molecule on the left, the ethanol, it's got an oxygen, a highly electronegative oxygen, way over on one side. That's going to pull the electrons over to the right side of the ethanol. That's going to make the right side of the ethanol more negative and the left side more positive. So that's going to be very polar. Now, the dimethyl ether may appear to be very balanced, where the oxygen also has an oxygen, but it's right in the middle. That might appear to be very balanced, but we're going to see something here in a second. So we would definitely say the dipole-dipole of the ethanol is stronger. And then a third factor is that the ethanol has an OH bond. That means it can hydrogen bond with another ethanol molecule. So therefore, it has dipole-dipole and hydrogen bonding, whereas the dimethyl ether, let's see whether it has dipole-dipole. It might, but it definitely does not have hydrogen bonding, okay? So that's going to be our explanation for the ethanol. So let's see the answer here. Ethanol has a higher boiling point, which means it has stronger intermolecular forces because of the asymmetrical lopsided oxygen on one side. The molecule is polar and can have dipole-dipole intermolecular forces. Also, the oxygen-hydrogen bond can produce a hydrogen bond. Okay? Now, let's look at the dimethyl ether. Dimethyl ether might look flat and symmetrical, but notice the oxygen has a steric number of 4, meaning that it has a tetrahedral domain geometry, and it has an AX notation of AX2E2. That's the same as a water molecule. So it's tetrahedral and it's bent. It's going to be an actual bent molecule. So even though it looks flat, it's a bent molecule. So it does have dipole-dipole forces because it is polar, it's bent, just like water. It cannot, however, hydrogen bond because there are no OH combinations. Okay, so a lot to think about there, and this is the way they like to present advanced placement questions. Okay, so hydrogen bonds of water, H2O, are stronger than hydrogen bonds of ammonia, NH3 or HF. Why is that? Well, if you look at water there is one hydrogen on a water molecule for each lone pair on other water molecules, a perfect match. So notice each water has 2 protons and 2 lone pairs. And so when you get a bunch of them together, it's a perfect match of 2 protons, 2 lone pairs. If you look at ammonia here, ammonia has only 1 lone pair for every 3 hydrogens, protons. Okay, so you see for those 2 protons, there's no lone pair to attach to. So it's a mismatch. If you go over to hydrofluoric acid, it has only 1 hydrogen proton for every 3 lone pair. So again, there's no hydrogen protons to bond with those 2 lone pairs, so again it's a mismatch. So because water has a perfect 2-to-2 matchup, it's going to have stronger hydrogen bonds than either ammonia or hydrofluoric acid. So water, hydrogen bonds most efficiently and has the strongest hydrogen bond. Hydrogen bonds occur when a hydrogen atom is bonded to the 3 most electronegative second row elements, which are nitrogen, oxygen, and fluorine. When oxygen pulls the electrons of a hydrogen toward it, a proton is left exposed. So that proton of that hydrogen is sticking out there because the nitrogen, oxygen, or fluorine has pulled the electrons really tightly to it. So this proton is attracted to the lone pair of another molecule with nitrogen, oxygen, or fluorine. The hydrogen atom has a fairly strong attraction to the other atom, though it is not nearly as strong as its own covalent bond. All right, let's look at some examples here. The diagram below shows a series of bonds and intermolecular forces. Identify which, the numbers 1 to 5, are hydrogen bonds. So let's look at number 1. It's a hydrogen covalently bonded, that's the solid line, to an oxygen, okay? So that is not a hydrogen bond, that's a covalent bond. So the answer to that is no. A solid line between hydrogen and oxygen represents a covalent bond, okay? How about number 2? There you have a hydrogen covalently bonded to an oxygen, the same one we just saw, and it's attracted to the lone pair of a nitrogen. So that fits the definition for a hydrogen bond. So yes, a dashed line between a hydrogen and a nitrogen is an IMF. Since the hydrogen is covalently bonded to an oxygen, this is a hydrogen bond. Okay, look at number 3. Okay, so you have a hydrogen covalently bonded to a carbon, and its intermolecular force is attracting it to the lone pair of an oxygen. Well, carbon is not one of the 3 atoms. It's not a nitrogen, oxygen, or fluorine. So that would not be a hydrogen bond. So no, the hydrogen has an IMF with the oxygen, but the H is covalently bonded to the carbon, so that would not be a hydrogen bond. Okay, how about 4? So you got again, the same situation. The hydrogen is intermolecularly attracted to the fluorine, but it's covalently bonded to a carbon. That's illegal. It can't be a carbon. Okay, so no. The hydrogen has an IMF with the fluorine, but the hydrogen is covalently bonded to carbon. Finally, number 5. There you have hydrogen that's covalently bonded to an oxygen, and it's attracted to the lone pair of another oxygen, so that's legal. That would be an intermolecular force. Finally, here's the 5th type of intermolecular force. It's called a dipole-induced dipole interaction, and it occurs when a polar molecule, permanent dipole, that's like water, approaches a nonpolar molecule, such as Br2, bromine, a bromine molecule, and pushes the electrons away, causing the nonpolar molecule to have a temporary dipole, similar to a London dispersion force. So let's go ahead and see that. In the example below, the oxygen side of the water molecule has a permanent dipole. Water is a permanent dipole, permanent positive-negative side. As it approaches the nonpolar bromine molecule, the electrons in the bromine are repelled to the right, causing a temporary positive dipole on the left side of the bromine and a temporary negative dipole on the right side of the bromine. So it looks like this. Here's the animation. And that pushes the electrons over to the right side. So in the if the water molecule is removed, then the electrons in the bromine will return to an evenly distributed nonpolar state. All right, and that takes care of a little bit of a lengthy lesson, but these are all 5 of the types of intermolecular forces that we'll be talking about in this unit.